Galaxies are colossal systems, some stretching over hundreds of thousands of light years, containing hundreds of billions of stars. They swirl with gas, dust, black holes, and something more elusive, dark matter. But here's the fundamental question. How do we know how much mass is in one? We can't simply place a galaxy on a scale. We can't just count stars and add up their weights. So, what do we do? Surprisingly, we don't need to see everything to figure out how much there is. What we need is motion. In this video, I'm going to try and explore how scientists measure the mass of galaxies. We'll cover the physics, the observations, and the surprises, some of which reshaped modern astrophysics entirely. In everyday terms, weight is a force, the pull of gravity on an object's mass. In astronomy, though, when we say we're weighing something, we really mean estimating its mass, how much actual matter it contains. But how do you determine mass when you can't touch or see most of it? That's where gravity becomes useful. We measure mass by observing how objects move under gravity's influence. Newton's law of universal gravitation tells us that the gravitational force equals g, Newton's gravitational constant, times mass 1 times mass 2 divided by the square of the distance between them. But more practically, we can measure orbital speeds. When an object is orbiting something massive, the speed of that orbit tells us how much mass is pulling on it. We've used this method to weigh the sun for centuries. We know the Earth's distance from the sun. We can measure how long it takes to complete one orbit. From that, we calculate its orbital speed. Then we use this formula. The orbital velocity equals the square root of g times the mass divided by the radius. Solving for mass gives us mass equals the velocity squared times the radius divided by g. For Earth, v is about 30 kilometers per second, r is about 150 million kilometers. Plug those in and we get the sun's mass, roughly 2 times 10 to the 30 kilograms. And that's how we weigh the sun, from 150 million kilometers away. Now let's scale that up. In a galaxy, stars orbit the galactic center due to the combined mass of everything inside their orbits: stars, gas, dust, and more. So if we can measure the speed of a star's orbit and how far it is from the center, we can calculate the galaxy's mass inside that radius. But galaxies aren't neat, clean systems. There's no single central mass like the sun. Instead, matter is smeared out, spread throughout the disk, bulge, and halo. And when scientists try and weigh their galaxies this way, the results didn't match expectations. In the 1970s, Vera Rubin and Kent Ford studied the rotation of spiral galaxies. They expected to see stars farther from the center moving more slowly, just like planets in our solar system. Instead, they found that orbital speeds didn't drop off, they flattened out. That was unexpected. According to Newton's laws, if you move farther out, your orbital speed should decrease, unless more mass is added at larger distances. But there isn't enough visible matter to explain this flat curve. The outer stars are moving too fast for the amount of observable mass. Rubin's work led to a groundbreaking conclusion. Galaxies must contain a vast amount of invisible mass. And that was the start of dark matter. The only way to make the math work is to assume that each galaxy sits inside a massive halo of dark matter, matter that does not emit light but does exert gravitational force. So let's return to the formula. If V stays high even at large r, then the inferred mass must keep increasing. But visible matter doesn't increase out there, so the missing mass must be something we can't see, which is dark matter. In many galaxies, dark matter outweighs visible matter 5 or 10 to 1. And it's not just Rubin's work. Astronomers have mapped rotation curves of hundreds of galaxies, and the pattern repeats over and over. There's another way to weigh galaxies, and that's by using gravitational lensing. Einstein's theory of general relativity tells us that mass bends spacetime, and that bends the path of light. If a galaxy lies between us and a distant light source, it can distort the light into arcs or rings. This distortion depends on how much mass the foreground galaxy has. By measuring the lensing pattern, we can calculate the mass needed to produce that distortion. It's another form of weighing, but using light instead of motion. And once again, we find that galaxies weigh far more than what we see. One of the strongest pieces of evidence for dark matter comes from the bullet cluster, which is a collision between two galaxy clusters. When they collided, the gas clouds slowed down and heated up, but the bulk of the mass passed through unimpeded. How do we know? Because gravitational lensing shows that the center of mass is not where the gas is, it's with the galaxies that passed through. This tells us that most of the mass isn't in the hot gas, it's in something that doesn't interact much, which is something invisible. This natural collision effectively split visible matter from gravitational mass, and the only explanation that fits is dark matter. Another technique is to compare how bright a galaxy is to how massive it appears from other methods. This gives us a mass-to-light ratio. For stars like the Sun, that ratio is around 1. That is, the Sun has a mass and light output that match. But for entire galaxies, especially larger ones, the ratio can be 10, 100, or even more. That means most of the mass is not shining. This method is useful in large galaxy surveys. Even if we can't resolve any star, we can still estimate the total mass and see how much light is being produced. So, how do we weigh a galaxy? We observe the motions of stars and gas, we apply Newton's laws calculating mass from orbital speeds, we observe how light bends around galaxies due to gravitational lensing, and we measure how much light a galaxy emits and compare it to how much mass must be there. All of these independent methods agree. There's more mass than meets the eye. Weighing a galaxy doesn't just tell us about the galaxy, it forces us to confront something deeper. The majority of the universe is made up of something we cannot see directly. Measuring the mass of a galaxy comes down to interpreting motion and light. It's a data-driven process rooted in tested physics. From orbital velocities to gravitational lensing, each method yields a consistent result. Galaxies contain significantly more mass than we can directly observe. These measurements don't just weigh galaxies, they point us toward one of the biggest mysteries in cosmology, the true nature of dark matter.